Hi, we are Team 11, and our topic is analyze and redesign of a food processor. The product we have chosen is the food processor, which is a kitchen appliance that is used to chop, mince, shred, and slice foods. It also has a wide variety of usage beyond cutting food like kneading dough and grating, using different attachments. Here is an exploded view of the entire food processor with a close-up on the blade shaft subassembly on the right. The estimated production volume for both primary and secondary customers is 900k units per year, where the primary customers are home cooks and secondary customers are professional chefs and other kitchen staff in the restaurant industry. Here we analyze the product and divide it into several sub-functions, like cutting food, mixed food, and also storing food, and further narrow down to specific functions. From the table, we can see which functions are the most important, such as pushing mixture, incorporating ingredients, providing protection, and facilitating cleaning. We can also see which functions are less significant, such as measure amount and displaying warning, as they only have one component representing it. And as a result, we came up with two tables, the functional differentiation table that divided in the commonality of function usage, and component commonality table, which separates the common parts and changeable parts. For product family, we focus on two parts. First is the blade design by having two extra blades, and the second is a full bowl redesign for a different volume. Here's how it looks when assembled together. For the assembly sequence, both the primary and secondary are the same. The product family will just substitute the parts without changing any sequence.
Here is our design for manual assembly. It takes around 153 seconds to assemble 26 parts together. With a theoretical minimum number of parts of 17, this assembly time drops down to 99.85 seconds, meaning our current assembly is only 65.2% efficient. We also decided to redesign the housing from the blade shaft subassembly due to its high assembly cost and functional importance as mentioned in our quad chart. We also decided to redesign the blade due to high assembly time. They were also chosen because other components are dependent on their design, increasing assembly time. The new housing design consolidates and reduces part count, has a locating feature for the blade, and adds taper for easy insertion. The new blade design consolidates and reduces part count, has a snap fit, and reduces fasteners. The new design reduces assembly time by 62.29 seconds, has no effect on product function, and reduces manufacturing costs by removing fasteners.
Next, we will look at our design for automated assembly, and for this section we have chosen to redesign the switch subassembly. So in the table, as you can see, it is comprised of four main parts: the electronic housing, the switch bottom plate, the switch itself, as well as the switch top plate, and in total it takes 7.62 seconds to assemble all this together. The electronic housing is too big, and that is why it is manually assembled. The first feature redesign was on the electronic housing. Extrusions were added with draft angles, and these will aid in the insertion of the other parts. When looking at our quad chart, parts with both high assembly cost and functional importance include part 12, which is the blade shaft subassembly. However, this was already redesigned in manual assembly section to be one part. The switch subassembly is another assembly that exists within our product, and all have the same function of provide protection. It is important to redesign the system to increase consistency, as safety is an important attribute of our product. This is the exploded view of the CAD model that includes the redesigned parts. Additionally, there is the updated assembly cost chart, and the final price of the redesigned subassembly came out to be 6.96 cents per part. The third feature were additional bores on the underside of the top plate. These coincide with the redesign of the electronic housing to simplify the insertion of the top plate. The second feature was an addition on the bottom plate, which is a pocket in the shape of the electronic switch. This will allow the switch to be easily inserted, as well as keep it steady after insertion. This comes out to be 8.6% cheaper than before the redesign. The effect is nowhere near as large as the manual redesign, but these are still adequate savings nonetheless. The added features should not have any impact on product function. However, the addition of them slightly increases the amount of material used to manufacture the parts, though the increase in material cost should be more than compensated for by the assembly cost decrease.
So here's our process selection. The first part is the blade. The most critical features are the blade and the snap feed mechanism. These features are critical as the blade is responsible for adjusting size and adjusting shape as stated in the FCMM. The blade could be too brittle or dull depending on its thickness. The snap feed may not function properly if the dimensions are off. The features should have a tolerance of plus or minus 0.1 millimeter, as the snap fit mechanism is responsible for holding the blade in place while it's spinning in high speed. So we run through all the requirements. Material is the stainless steel, and shape is sheet. And we also have our mass, which is 0.012 kilogram, and our thickness, which is 2.2 millimeter. The tolerance, as stated, is 0.1 millimeter, and we decided our roughness to be 0.6 micrometer. And here's our batch size, which is 900K. And this is our final table. As you can see, the only one that fulfill all the requirements is machining. We have chosen stainless steel for our material because of its food safe properties and common usage in other food cutting products. Okay, now the second part is the housing. The most critical features are the pin at the top and gear inserted at the bottom, as it allows the housing and blade to stay in alignment. This alignment is critical as the housing is responsible for pushing mixture, as stated in the FCMM. Misalignment may result in part of the mixture to stay in place. And the tolerance is as low as the blade because we wanted as little room for play in the system as possible. And we run through all the requirements: material, shape, mass, thickness, tolerance, surface roughness, and batch size. And we got our final table. As you can see, the final two candidates are machining and injection molding. Given the manufacturing time and cost, we decided to go with injection molding. We also have chosen ABS for our material for its food safe properties and economical manufacturing cost.
We performed a machining cost estimation for our blade before redesigning for DfM. As shown here, with part production time, non-productive time spent, and tooling considerations, the estimated cost per part was $6.39. Using DfM Pro, we analyzed our part and looked at some of the recommendations in order to facilitate our design changes. As seen here, this is our new blade design while accounting for manufacturability. The three rules we used were DfM C-3 with standard dimensions, DfM C-7 to place features away from edges and corners, and DfM C-14 showing the flat sections to facilitate fixturing. You can see here on the right the before and the left for after for direct comparison. After redesign, we analyzed the estimated cost per part to $5.78. As comparison, most of the cost reduction lies in the lower estimated production time per part. After inputting our pre-designed and post-redesigned parts into hubs, we can see the relative price comparison from our estimated model to the hubs quote. This is assuming the 900,000 production volume, and we reduce the hubs quote by 20% to account for profit margins as well. Moving on to the housing, we can see before our redesigning part is estimated at 45 cents per part. After some high importance DfM Pro suggestions, we redesigned our housing units. As seen here, we used DFIM-5 to account for an increase in rib thickness. We also added draft angles to the longer shaft sections and incorporated uniform wall thickness to facilitate faster and more uniform cooling during injection molding. From analysis of our post-processing design, we can see an 8-cent decrease in cost per part. This total number is relatively low due to the large batch size and cost effectiveness of injection molding, but some unseen cost savings such as easier part release, decreased cooling time, and more uniform higher quality parts are also a result of our redesign.
For product service system, we decided to use product-related service, which is conducted in terms of warranty for repair and also replacement. By using this PSS system, customers will have higher expectations, which will lower their hesitation when choosing between competitors' products. Also, this system could recycle the failed products and also reduce the waste. To conclude, after redesigning, we managed to reduce the cost of blades and housings. Multiplied by the batch size, this will save around 621 grand for manufacturing alone. However, the wiggling issue still remains, and we could also reduce the base fixtures for optimal injection molding. Thank you for watching.